Hey guys, Mr. Bowman here. Today we are introducing triangular distributions. This is the third of our distributions, and we have two learning objectives. The first in green, we are learning to identify the three assumptions of a triangular distribution. And the next one that's going to become increasingly relevant, we are learning to identify the formulas related to a triangular distribution. So let's recap. Just down the bottom, that would be our x and y axes, and a triangular distribution, a distribution that is triangular in shape. Like we did for rectangular distributions, we always denote the minimum and the maximum with a and b. So I'm just going to write up the top here. So to do with that, we always have some parameters, and a, that is always to the minimum value of the triangle, and b, that is always related to the maximum value of the triangle. And for triangular distributions, we actually have a third parameter, c, which is the peak of our triangle. And just a reminder, often you would have x, and x relates to the shaded portion of your triangle. Relates to shaded portion of triangle. And there could be more than one x's as well of triangle. Okay. The next thing we want to go through is we just want to have a look at the features of a triangle and how we can link that to our assumptions or develop things to look out for a triangular distribution. So assumptions. And we have three assumptions. The first assumption, we are still dealing with continuous data. If the data is not continuous, it's a bit gray as to whether or not a triangular distribution will be appropriate. But we will be going through something called continuity corrections, which can get around that issue or that assumption. Number two, there is always a minimum and a maximum value. And that is because a triangular distribution is not like a normal distribution where it goes on forever. There is a fixed endpoint and a fixed start point, similar to a rectangular distribution. And the one that changes from rectangular distribution, for number three, it would have been something like all outcomes are equally likely, representing they're all the same way, the same distance away. But in this case here, we have one mode, and a mode is a peak or a point that is more likely to occur than the others. Point more likely to occur. And if you have those three assumptions present, then it looks good. A triangular distribution may be appropriate for you to use. And I'm just going to change pen color again. We are going to go on to the formulas, and like our assumptions, there are three formulas that we need to be aware of. The first one is the formula of the peak. So how tall would that triangle be? And that's similar to the normal or to the rectangular distribution one, just as a proof. So the area of a triangle is always equal to base times height times 1/2. The base of our triangle would have been b minus a times height times 1/2, and the area would be 1. If we move that times 1/2 to the other side, that becomes divided by 1/2, which is going to make it to 2. And if we simplify that, that would be 2 divided by b minus a, or to put it another way, 2 divided by the base of that triangle. So just going to write that down below. So the formula for that, the height. So the height formulas are the ones that we're interested in. How do we find the height? The base is always easy enough to calculate. We can just look at the x-axis. So the height, that is equal to 2 divided by b minus a, and the other way to put that was 2 divided by the base of that triangle. So I'm just going to pause the video to clear that working, and once that is done, we'll chat about something called the left and right slope formulas. Okay, so that's all cleared. The second formula we're looking at, so on erase mode, the second formula we're looking at is something called the left slope. And the third formula would be the opposite of the left slope, which is the right slope. Okay, so the left slope makes sense. If you think of the name, the left slope, that is how to calculate the height of any point on the left slope of that triangle. So for example, if we were trying to calculate the probability of this area, we would need to know the height of that triangle and the base of that triangle. So we need to find the height on a left slope of a triangle. So the height of this equation, so it's a bit more complicated. The height, it does refer to a lot of B's, A's, and C's, but the height would be equal to 2 times x minus a in brackets divided by b minus a and b minus c. And the height conversely, so if we were trying to find the height of a triangle, so for example, if we were finding that shaded area, we'll need to know the height at that point x. We'll then use the right slope. So here was the left slope, and on this side was the right slope. You would need to know the right slope formula, which is slightly different. 2b minus x divided by b minus a, b minus c. And if you were wondering how those formulas were come about, they used a concept called similar triangles to scale up and down the height based on its relative position along the left and right slopes. So hopefully you found this video useful. What you should be looking to do is from this video, you should be looking to get the diagram with a description of the parameters. You do need to be writing down the assumptions that are relevant to a triangular distribution. And you do need to be getting down those 3 formulas that are very, very, very useful for calculating the probability of given events under a triangular distribution model. Hopefully you found this video useful. Now, next step, let's start getting into some questions.